887,000 trucks. That's how many General Motors recalled in 2025 for engines that destroy themselves before 50,000 miles. 28,000 complaints, 14,000 complete engine failures, 12 injuries, 42 fires while families were driving. Ford's 3.5-liter EcoBoost is surging at idle, stalling at red lights, throwing check engine codes before 1,000 miles. Ram's new Hurricane engine is overheating and cracking blocks at 3,000 miles. That's not a coincidence. That's not bad luck. And it sure as hell isn't three separate manufacturing mistakes. Manufacturers ran the math. They figured out that paying for a few thousand blown engines was cheaper than paying the government $340 million a year in fines. So, they budgeted for your engine to fail. They put it on a spreadsheet, approved it in a boardroom, and shipped the trucks anyway. Compliance won. And you're the one writing a $15,000 check for their decision. Think about the guy who saved for years to put $75,000 into a new Silverado. Everything is fine for 18 months, until one morning he hears a knock under the hood, and by noon the engine is dead. The mechanic's estimate is $20,000 for a replacement, the parts are back-ordered for months, and he's still stuck making $1,200 payments on a truck that's just sitting dead in a service bay. Does any of that sound familiar to you? If you walk into any dealership service bay right now, you'll see the same thing. Trucks with the cabs pulled off, engines on stands, and mechanics shaking their heads. They're seeing failures that shouldn't happen for 200,000 miles, occurring before the first oil change. It's a scene that would have been unthinkable 10 years ago. Here's what genuinely bothers me. Engineers didn't suddenly forget how to build engines. What changed is the environment those engineers are forced to work in. And I'm going to show you exactly what that environment is. To understand why new engines are breaking, you have to first understand why old ones didn't. Take a truck engine from the early 1990s. Big, naturally aspirated V8. A 5.7 liter that made maybe 210 horsepower, thick cast iron components. Heavy 5W30 oil that coated every surface with a generous protective film. And the gap between moving parts was roughly the thickness of a heavy piece of construction paper. That space let a thick layer of oil sit in there like a cushion. If a tiny speck of dirt got in, it just floated around without touching the metal. Those old bearings also had a thin layer of lead on the surface. If a microscopic piece of debris made it past the oil cushion, it just embedded harmlessly into the soft lead and sat there. Oil pressure dropped for a split second on a cold start. The lead absorbed it. You could skip an oil change, run it hard in summer heat, tow more than you should. That engine had a wide hallway of protection, and it just kept going. Those engines are still out there today with 300,000 miles on them. Now, here's what modern engines look like. Turbocharged, downsized, and that same gap between moving parts has shrunk from the thickness of construction paper down to the thickness of a single human hair. Because the gap is so tight, the oil has to be almost as thin as water, just to flow through it. The lead is gone from the bearings too, replaced with harder aluminum alloys that can't absorb anything. Now, picture a microscopic piece of metal debris getting into that hair-thin gap. There's no oil cushion, no soft lead layer. That debris acts like a razor blade against the bearing surface, and the engine has no way to absorb it. You've gone from a wide hallway of protection to a tightrope where one speck of contamination ends the engine. Everything designed for forgiveness was stripped away. And here's where it gets worse. That hair-thin gap doesn't just demand perfect machining. It demands oil so thin it flows like water, and a perfect uninterrupted supply of it every second the engine runs. When you add a start-stop system that kills your oil pressure 50 times a day into that equation, you've got a recipe for disaster. We'll get into exactly how that trap works in a moment. But first, you need to understand the rule that forced manufacturers to build engines this way. Here's how they did it. Manufacturers figured out a trick. If you slap a turbocharger on a tiny engine, say a 2.7 liter, and crank up the boost pressure, you can squeeze 400 horsepower out of something the size of a suitcase. On paper, that sounds awesome. More power. smaller engine, better fuel economy numbers. But here's what nobody tells you at the dealership. That little 2.7-liter engine making 400 horsepower is producing more internal pressure, more heat, and more stress on every single component than that old 5.7-liter V8 ever did, with literally half the metal to handle it. We are talking cylinder pressures over 2,000 pounds per square inch inside that engine. That's race car territory. Think about it like this. A workhorse is built to pull a plow all day, every day, for years. It is not fast. It does not need to be. It is built for endurance, with the muscle and frame to handle a full day's load without breaking down. A racehorse is built to run at its absolute limit for 2 minutes. Everything about it is tuned for peak output, not longevity. When manufacturers started shrinking engines and bolting on turbos to make up the power difference, they took the racehorse and put it in the workhorse's job. The turbo gives it the power to pull the plow, but the internal parts, the bearings, the pistons, the crankshaft, those are still racehorse parts. They're screaming under a load they were never designed to carry for 200,000 miles. A racehorse being forced to run a marathon every single day with a full trailer hooked behind it. But engineers didn't choose this path because they wanted to. They were backed into a corner by a set of rules they couldn't win, and those rules are called CAFE standards, Corporate Average Fuel Economy. The federal government sets a mandatory miles per gallon target that every manufacturer's entire fleet has to hit or pay fines. $17 per vehicle for every tenth of a mile per gallon short. That sounds small until you do the math. Ford, GM, and Ram each sell around 2 million vehicles a year. Miss the fleet target by just 1 mile per gallon, and you owe $340 million, 1 mile per gallon. So that is the number sitting in every boardroom. $340 million on one side of the scale. It's a mathematical balancing act. For every heavy-duty truck they sell that gets 18 miles per gallon, they have to sell 3 or 4 tiny fuel-sipping cars or electric vehicles just to keep their fleet average from drowning. When they can't sell enough of those small cars, they have to force that fuel efficiency into the trucks themselves, even if it means compromising the very thing you bought the truck for, reliability. By 2026, the industry has to hit 49 miles per gallon fleet average. Your F-150 gets 20 miles per gallon. Your Silverado gets 18 miles per gallon. There is no mathematical way to hit 49 with traditional engines. So, manufacturers downsized everything, and the first thing they sacrificed was your oil. 20 years ago, most engines ran 5W30, thick enough to coat your bearings with a solid protective film. Then the fuel economy push got serious. Thinner oil flows faster through the engine, creates less internal drag, and technically improves fuel efficiency on paper. So 5W30 became 5W20, then 0W20, then 0W16. Now some of the newest engines on the market are speccing 0W8. Ford does it, GM does it, Toyota does it. Subaru specs 0W16 in the United States, but the exact same engine sold in Japan runs 0W20 to 5W30. Japan does not have CAFE penalties. That's not a coincidence. That's the policy showing up in your crankcase. 0W8 is so thin that if you poured it on your hands right now, it would feel almost like water. That is the only thing standing between your crankshaft and total destruction. But thinning the oil was just one move. To hit these impossible numbers, manufacturers didn't stop there. They stacked 6 specific technologies on top of each other: cylinder deactivation, start-stop, direct injection, variable oil pumps, extreme turbocharging, and manufacturing shortcuts. Each one shaving off a fraction of a gallon on a government test, but together creating a perfect storm that destroys long-term reliability. We're going to break down exactly how those 6 killers work in a moment. But first, you need to see the specific engines that are already failing right now. Then the other side of the scale: warranty repairs, recalls, settlements on engines that fail early. They ran those numbers too, and the calculation came back clear. Paying out warranty claims on a predictable failure rate was cheaper than missing the target, so they shipped the engines anyway. Your engine's lifespan versus their compliance. They chose compliance. If you think the industry-wide shift is bad, wait until you see the specific evidence. Because right now, there are 3 flagship engines destroying the life savings of American truck owners. Start with GM. The 6.2-liter V8 is their flagship. This engine powers the Silverado 1500, Sierra 1500, Tahoe, Suburban, Yukon, and Escalade. In April 2025, GM recalled 887,000 vehicles. The problem is machining debris combined with crankshaft journals produced outside of specification. When you combine those two things in an engine running 0W20 oil with micron-level clearances, the main bearings start failing. The failure pattern is catastrophic. Complete bearing collapse. Connecting rods throw. The engine destroys itself from the inside out. The numbers tell the story. GM logged more than 28,000 complaints about these engines. Out of those, 14,000 resulted in complete engine failure, total loss of power on the highway. The NHTSA data includes 12 injuries and 42 fires. 42 engines that literally caught fire while families were driving. One owner brought a 2021 Silverado in at 56,000 miles after hearing metal grinding. The dealer confirmed main bearing failure. Replacement cost out of warranty runs $15,000 to $20,000. GM's recall fix is to switch the oil to 0W40 and hope that solves it. Ford's 3.5-liter EcoBoost twin-turbo is taking a different hit. Starting with the 2026 model year, Ford is reducing this engine by 18 horsepower, from 400 down to 382. Why the power loss? A new gasoline particulate filter to meet California emission standards. This filter traps soot and needs regeneration cycles at highway speeds. But here's the problem. If you do mostly short trips without highway driving, the filter never reaches temperature to burn off soot. It clogs. Check engine lights. Forced regeneration at dealers. Owners report surging at idle, stalling at red lights. Check engine codes before 1,000 miles. One F-150 PowerBoost owner spent 10% of his vehicle's life at the dealership in 30 months. The transmission and hybrid system added another layer of complexity that compounds every problem. Ram replaced the proven 5.7-liter Hemi with the Hurricane inline 6 twin-turbo starting in 2024. This was supposed to be the answer: more power, better efficiency. Instead, thermostat failures are causing catastrophic overheating. One Ram RHO owner experienced complete engine failure at 3,000 miles when the thermostat stuck closed. The engine cracked the block. Ram issued a technical service bulletin confirming defective thermostats from suppliers. Sediment contamination in production runs. When an engine can't cool properly, it destroys itself in minutes. The telling part is that Ram announced they're bringing back the Hemi for 2026 because Hurricane sales are collapsing. When a manufacturer revives an older engine, that's a massive red flag about the new one. The 2021 through 2024 model years need their own category. These are the zombie years. Engines built during COVID supply chain chaos are now hitting 60,000 to 100,000 miles. That's exactly when hidden manufacturing defects become catastrophic failures. Those factories were running skeleton crews. Quality inspectors were gone or operating at reduced capacity. Normal validation protocols were thrown out. GM struggled with out-of-spec connecting rods. Ford had similar supplier issues. Warranty complaints are spiking right now because those engines are hitting their failure point simultaneously. We're living through the delayed consequence of 3 years of compromised manufacturing, all surfacing at the same time. If you are buying used today, those zombie years are a minefield a clean Carfax cannot help you navigate. Here are the 6 killers we have been building toward. None of these technologies was designed to destroy your engine. Each one was designed to shave a fraction of a mile per gallon off a government test. But when you stack all 6 onto the same engine, running at race car cylinder pressures with water-thin oil and micron-level clearances, you get exactly what we are seeing right now. Start-stop. Technology forces 40 to 50 restart cycles per city commute. Every restart is a dry start event with 0 oil pressure. Cold starts cause the majority of total engine wear across a vehicle's lifetime. Fleet trucks that rack up 150,000 highway miles often outlast personal trucks with 50,000 city miles. The difference is not the odometer, it is the number of start cycles. With 0W20 oil and micron tolerances, every single restart is a micro-wear event on bearings that cannot tolerate it. Variable displacement oil pumps adjust output based on engine load. Sounds efficient, but it means your oil pressure is not constant anymore. Combined with start-stop cycles, bearings run with less protection than they used to. Direct injection systems spray fuel at 2,000 to 3,000 pounds per square inch directly into the combustion chamber. Higher pressures mean more thermal stress. No fuel washing the valves means carbon buildup. A thinner oil film under higher combustion temperatures accelerates wear. Cylinder deactivation turns V8 engines into V4 engines under light load. That creates uneven temperatures across the block, uneven expansion and contraction. Shock loads occur when cylinders reactivate under acceleration. The thermal stress is something older engines never had to handle. Turbocharging at extreme levels generates cylinder pressures over 2,000 pounds per square inch. That is race car territory. A 1990s naturally aspirated V8 made 210 horsepower from 5.7 liters, roughly 37 horsepower per liter. A modern 2.7-liter turbo makes 325 horsepower. That is 120 horsepower per liter. Same stress, half the metal to absorb it. Manufacturing debris, the microscopic metal particles left during machining, gets trapped in tight oil galleries. Professional engine builders spend hours cleaning every passage. GM builds 10,000 engines per day. One microscopic piece of swarf between a bearing and journal acts like sandpaper spinning at thousands of RPM. Stack all 6 factors together, and you've built an engine where everything has to work perfectly every single time, across millions of operating cycles. At mass production scale, that's not achievable. The failure data proves it. The deck is stacked against you, and the manufacturers have already moved on to the next quarter's profits. But you aren't helpless. Here is your survival guide to keeping your truck out of the scrapyard. Check your vehicle identification number at nhtsa.gov immediately. If you're inside a recall, schedule the repair now. Cut oil intervals in half. Hit 5,000 miles regardless of what your manual claims. Disable start, stop every single drive. A $50 OBD2 module disables it permanently. After warranty expires, step up one oil viscosity grade. If buying used, avoid 2021 through 2024 turbocharged engines. A 2016 through 2019 naturally aspirated V8 with honest highway miles beats a 2023 turbo with 30,000 city miles. This isn't bad luck. It's a calculated business decision about your engine's lifespan, and you paid for it, but that doesn't mean every truck on the lot is a ticking time bomb. I've narrowed it down to the only gas engine worth buying now that isn't built on a compromise. Watch that video right here to see which one actually made the cut.